to move from England to Wales. We take a train from London to Abertower.
More or less,
Abertower.
yes, yeah.
And our last but not least speaker is Tomasz I'm sorry, these Welsh names are so tough to pronounce. Tomasz Brzezinski. And he will tell us all and more about non-commutative geometry of generalized Weyl algebras. Take it away.
Okay, thank you. So first of all, I would like to thank the organizers for inviting me here and giving this chance to give this talk. And since this is the last talk of the conference, as it seems, I will, okay, so I had some message from the chairman that I shouldn't do what I was planning to do, so I will follow the chairman, but thank you. It's from all speakers to the organizers. Okay, right, so I will be talking about my recent work. Partly it's a work done in collaboration with Nicola Ciccoli, Ludwik Dąbrowski and Andrzej Sitarz. Polish names are difficult to pronounce. And partly it's my own work. And it's really about some description of, algebraic description of Dirac operators and with some reality structure on a particular class of algebras which are known as generalized Weyl algebras. Right, so let me begin with the beginning, as the people say in Swansea. Right, so really the work includes those Dirac operators and the real structure on them, and they are not. There are some twists in the story. So some time ago, nearly 10 years ago, Kohn and Moscovici introduced twisted Dirac operators. They are twisted by an automorphism, and the commutators are twisted. And very recently, Gianni Landi and Pierre Martinetti studied twisted real structures for such twisted triples. However, more or less at the same time, or maybe a bit earlier, or more or less at the same time, I was visiting Ludwig in CISA, and we started working on trying to construct Dirac operators for non-commutative for quantum cones. And we realized that there is also twisting there if we want to introduce a real structure. And next I met with Andrzej somewhere in Poland, and he told me that they encountered in his work with Nicola Ciccoli, they encountered such a twisting for real structure, really for standard Dirac operators. So we combined our forces and came up with the idea that sometimes it appears that even if you are dealing with the untwisted commutators for the Dirac operator, if you want to introduce the reality structure there, then you need some twists. And the perfect examples of this, where such a twist is indeed seems necessary, are quantum generalized Weyl algebras, which were introduced some 20 years ago now by Vladimir Bavula. Okay, so let me explain purely algebraically what does it mean to twist the reality. So first of all, we start with a complex star algebra and the representation of this algebra. The algebra is B, representation of this algebra. And D is some linear operator, which will play the role of the Dirac operator. And nu is a linear automorphism of the space or module on which B is represented. So if you have such a linear operator, you can lift such an operator to an algebra automorphism on the endomorphism rings of such vector spaces. And here is the procedure, how you can do it. So you just conjugate your linear maps by this automorphism. Okay, and then this, in such a setup, one can say that triple BHD, which consists of this algebra represented on the space H, operator on H, admits a new twisted real structure if there exists an anti-linear map which squares to some sign. So it's identity up to the sign depending on the dimension. And for all A and B, it satisfies the following conditions. So the first condition is just a standard zero-order condition. There is no twist there. All the commutators are non-twisted usual commutators. The twists start appear when we discuss the first order condition. So the representation, the way that elements are represented as endomorphisms of H needs to be twisted. And also the commutators between D and J and the commutators have to be twisted by the automorphism. Again, it's a commutator or anti-commutator depending on the sign. If we are dealing with an even situation, so if there is a grading operator, then also it has to react somehow with the twists. And here are the rules by which it has to act with the twist. Okay, this just commutes with J. There is no twist there, but there is this relation which connects. So it's gamma is stable under the conjugation by nu squared. Okay, again, epsilon prime is another sign which we can determine depending on the dimension, KO dimension of the triple. Okay, so that's a general definition, purely algebraic. I will not talk about analytical aspects. It will be purely algebraic talk. Now let me give you a construction in which one can encounter such Dirac operators with the real structure which is twisted by an automorphism. And the construction comes from algebras, well, from graded algebras, algebras graded by groups. Okay, so suppose that we have a group, let's say discrete group, so it's countable group, and we can consider a graded algebra, so which means that it's as a vector space, it's graded by degrees corresponding to elements of the group. If you multiply two elements of degrees g and g prime, you will get an element of degree g prime. Star grading means that there is some compatibility between the star. If you have an element of grade g and you look at the star of this element, you will get an element of degree g inverse. Okay, so there's a compatibility of the grading with the star structure. That's what I mean by star graded star algebra. Okay, so that's what I actually explained there. That's this compatibility condition. Now, this ensures, first of all, that the degree of the homogeneous part of the algebra A, which corresponds to the degree equal to the neutral element, is itself an algebra. And this condition on the star ensures that the star operation restricts to B. Okay, so now what we do with this graded algebra? Well, we select two subsets of our group. So first of all, we select one subset, and the other is determined by the selection of the first one. So we select some elements, and then we complement the subset by creating a set of all inverses of the selected elements. And then we split or consider two parts of A, just combining the elements of degree in both subsets that we have. Okay. Now, what I should have mentioned is that because B is a subalgebra of A and it's a subalgebra of degree 0, there is a natural action of B on all homogeneous elements, say, of degree G. So B will act on H plus minus just by multiplication.
Can you say again what is G plus?
Just a subset of G, any subset. So for this construction is an any subset. I will give, well, non-empty.
But you want direct sum, so you want G plus and G minus to be disjoint?
So the condition is that G plus and G minus are disjoint. Yeah. So so they are not completely free if you should not include in G plus inverses of the elements in G plus.
So where is B
There is no B there, not necessarily there. B just acts, so it's not included there. B will act on H plus minus. Okay, then what we need to do, we select a graded automorphism, so the degree-preserving algebra automorphism of A, which satisfies some condition relating to the star, so-called regularity condition. So this is not new. It's not a star algebra map. It's an algebra homomorphism or automorphism, a graded algebra automorphism, but it does not commute with the star operation. It satisfies this regularity condition. What we need next, we need to construct some operators on A, so-called twisted mu square, twisted q plus minus square skew derivations. The squares that appear there are for convenience. Q is just a number, element of your field, and I will need the square root of q, so that's why I decided to, at some stages there will be square root of q, so square root of q squared, so I will go back q, okay?
So in this condition with the star is like for the antipode in the star of algebra, right?
Yes. Yeah. But the antipode is not an algebra map. But
Sure.
okay, so those maps d plus del plus minus, they have to satisfy some twisted Leibniz rule. So that's why they are called nu square twisted derivations. And this q plus minus 2 conditions q derivation property means that they are not only satisfy this Leibniz rule, but we also have this additional condition. As I later on, I will give you the examples, concrete examples where this happens. Okay, so we have this real number q, not equal to 0, of course. Otherwise, I wouldn't be able to take its inverse. Okay, so that's all. We are almost there. Now we need to assume some compatibility conditions between all the structures that are involved, between those skew derivations, automorphism, and the star structure. So here you have one condition, which relates nu with star and dels. And also what we need is that the subspace H minus goes transformed to H plus if I apply del plus to it, and if I apply del minus to H plus, I will get H minus. Okay, so there is some movement between H plus and H minus when you use those Q derivations. Next, what I will do, I will view H as a left B module, but not by the multiplication, but the multiplication twisted by nu squared. Okay, so as I explained, B acts on each of the components, homogeneous components of A, of the algebra A, just by multiplication. And now what I'm doing is I'm twisting this, I'm introducing action with a twist. Okay, so if we have this construction that one can prove that this kind of Q-Dolbeau Dirac operator with the grading and the real structure is an example of the Dirac operator with the new twisted real structure. Okay, so it looks like a very complicated procedure. There is a natural way of obtaining such operators, and the natural way which will be explained on the next slides in the particular examples of generalized Weil algebras, really makes use of quantum principal bundles that appear there. So the grading in all examples that I will give is a particular type of grading, so-called strong grading, which corresponds to the Galois condition, and it's an example of, this will be examples of bundles non-commutative bundles, principal bundles with finite structure group and with a group U1. Right, so now let's have a look at those examples. Oh, before I go to examples, I want to explain that whenever you have this kind of system of skew derivations, not necessarily Q-skew derivations, you can construct at least a first-order differential structure. Well, you may construct, but it's not necessarily always possible. So let me give you a precise meaning of this statement. So first of all, what I mean by a first-order differential structure is this. So we have an algebra. We have a bimodule over this algebra, together with a bimodule valued derivation of this algebra, so a map, linear map, which will satisfy the Leibniz rule. No twists there, just the ordinary Leibniz rule. So we have a bimodule with a bimodule valued derivation of an algebra. Now, to talk about differential calculus, we need to impose another condition, and this is a so-called density condition.
Which topology?
Well, it's an algebraic density condition, which really okay. So right. So the condition is that every element of the bimodule can be written as a finite sum, linear combination of elements of the type A, D, B. Okay, because of the Leibniz rule, it's the same as saying that we have dA, B decomposition, or the mixed ways of writing those elements. And the reason why one should impose such a condition is that to have something which really tells us, gives us some information about the algebra itself. Because if I just stopped at A, there is very little information about the algebra itself. Because whenever you have a module, you can always extend it trivially to something bigger. And you can say, well, D acts trivially on the, there's no part in this additional component, and then we will end up with something which does not tell us much about the structure of algebra. So this condition B is very important because it relates directly the module that we select with one forms with the structure of the algebra. Of course, if the algebra is a star complex algebra, complex star algebra, then we would like to have a star structure on the calculus, which means that we can extend this star operation to the bimodule, and the star operation will mix left with right multiplications. And it will commute with D, so D will be a star operation. Starting with such data, you can always extend this to the full differential graded algebra. If you have the star structure, you end up with the star differential graded algebra. There is no, it's not, the way of extending this is not unique. There is a minimal way, which takes into account that you have to have a nilpotency of D if you extend it to higher forms and the graded Leibniz rule. But there is no unique way of extending this. But anyway, I will stop only at the first differential calculus. And the reason for this is that if you have a system of skew derivations, twisted derivations, so you have derivations di, some indexing set, and finite indexing set, and derivation del I and nu I, so the Leibniz rule for those dels is twisted by nu I, then you can do the following construction. You construct a free left-A module with a, so it's called the basis of this module omega I, so it will have the same rank as the size of the indexing set I. This module will not be, so then if you want to introduce the bimodule structure, you introduce the multiplication from the right by using the multiplication from the left, but after applying the corresponding automorphism. And then if you do this, and you write this map D, then you can check that this map will satisfy the ordinary Leibniz rule.
What is a free basis?
It's a free module, so it's a basis of a free module. Okay.
Free basis and non-free.
Well, in a free module, you can find a set which will be well, not quite, because there is a dual basis in the projective module, and you cannot find it. It's also a basis, but it's a dual basis. So in a module situation, you have to differentiate between. So it's a free set of generators, if you like, of the module. Okay. Okay, so if you do this construction, you will have this module graded derivation. But in general, there is no way of ensuring that the density condition will be satisfied. Okay, so you need to select the proper, you make the proper choice of skew derivations to find out that that you actually have a calculus. Okay, and this construction, of course, will give a calculus in very specific situations, because the cotangent bundle, if you think about it in that way, or sections of the cotangent bundle will be free module. So this cotangent bundle should be trivial in this case. So this will be, this is the way you can construct differential calculi, for example, on quantum groups. And actually, there is a opposite procedure. If you have such a module with a simple structure and D, you can recover this del i's. Right, so now the class of the algebras which are in the title. So the idea of this generalized Weyl algebra is the following, that we start with an algebra. We select an automorphism of this algebra and an element in the center of the algebra. And then what we do, we construct a bigger algebra by adding two generators and particular rules between the generators. Okay, so we extend our algebra by two generators, and they satisfy these rules. P is an element in the center of A, and sigma is an automorphism. Okay, so whenever you commute these two new, whenever you hit these two new element generators, you will get P or the sigma of P, depending on the order. And whenever you commute new generators with elements of A, you will get a twist by non-commutativity encoded in this automorphism. And it turns out that such algebras share many properties of the algebra A. So for example, if A is a Noetherian algebra, then so will be its extension. If A is a domain and P is not equal to 0, then this generalized Weyl algebra will also have no zero divisors. Obviously, if P is 0, then we'll have Y and X will be zero divisors. So one can also show more that some homological properties which are preserved. So for example, if you start with if your A is an algebra of polynomials in one variable, then you can show that if P does not have, so P is just a polynomial, if it does not have repeated roots, then your algebra is Calabi-Yau algebra. So there are a lot of properties that these algebras will have, very nice properties from the algebraic point of view or non-commutative algebraic geometry point of view.
Any relation to the cyclic homology groups?
I don't know. Okay, so in fact, I will be only concerned with the algebras where A is a very simple ring. It's a ring of polynomials in one variable. So everything is central there. So I can choose as my central element. I can take any polynomial or any polynomial. Now, for the choice of automorphisms, there is a limited number of choices that I can make, and it's really labeled by two numbers. One is a non-zero number, that's Q, and one is just any number.
Is Q still real?
Not necessarily at this point. It will become real in a second, because I want to have a star structure.
Twist reality.
Yes. Yes. So, but it won't be twist real, it will be real. Okay? There's no twist in this reality. Okay, so if I write the relations, which I rather than using sigma, using this qz plus r description is linear transformation of z, then that's what we will have. Now, if P has a real coefficients and both Q and R are real, obviously Q is not 0, then we can make this algebra into star algebra by defining, well, saying that y star, so x star is the same as y, and z is equal to z star. Okay. Possibly there are other ways of making this into star algebra, but this is the way that I will use in my talk. Okay, so if you, it turns out that you can think about these algebras as some kind of models for non-commutative surfaces, or coordinate algebras of non-commutative surfaces. So, for example, quantum spheres, quantum Podley spheres, quantum weighted projective lines or spindles, they all are included into this class of algebras. Okay, among those Weil algebras, I will be particularly interested in one class, which I term regular generalized Weil algebras. And the point is that if I want to construct differential calculus, then it turns out that I need to have some separability condition for the polynomial that I use as my part of the structure of this generalized Weil algebra. Okay, so I will say that a polynomial is Q separable polynomial if the polynomial is coprime with its Q derivative. Okay, so this, if you look at the Q tending to 1, then you will get a standard correspondence between the separable polynomials and polynomials whose formal derivative is coprime with the polynomial itself. So that's hence the name Q separable. And I will say that the generalized Weil algebra is regular, provided R is 0 and P is a Q separable polynomial. Okay, so I will be only interested in the case when R is equal to 0. So if you think about Podley spheres, this is the so-called standard Podley sphere, which is the exceptional case of the family of Podley spheres. Right, so the regular generalized Weil algebras fall into two classes. The one class is that the polynomials which do not have 0 as a root. Okay, and so if we have a regular Weil algebra, generalized Weil algebra, then polynomial either doesn't have a 0 as root, or if it does have the 0 as a root, then it's a simple root. Okay, because if there is a say double root, then if you take the Q derivative, you will reduce the degree of the root, but the root will stay as there will be common factor with the original polynomial. So if it has a 0, it's a single 0. It's not as a root, it's a simple root. Okay, so typical examples are, in the first class, are quantum cone algebras. So the polynomial here is chosen in a particular way. Note that all the roots are separated, and that's why the separability tells us that it should be the case. And Q to the power n is, again, this high power there is just to avoid any fractions of Q in the fractional powers of Q in the formula. So it's just for visual reasons in a way. And algebras in class B include so-called quantum teardrop algebras. If you take n equal to 1, then you will get Podley sphere. Okay, it's our generalizations of Podley spheres. As you can see, the polynomials that appear there are very similar in a way. There's a product of those Q factors, and well, there is a 0 root in the second case, no 0 root in the first case. But these two classes split into, when you try to construct this twisted, Dirac operators with twisted reality via the twisted derivations or skew derivations, then they fall into two different classes, as we shall see in a moment. So in the case when, if I go back to the cone algebra, so now I will concentrate on the first class. So if I set n equal to 1, then what we will get will be just the quantum disk algebra. Okay, so when n is equal to 1, we have a quantum disk algebra. You might wonder what happened with our three generators. We had generators x, y, and z. But because the polynomial is just a linear polynomial, you can express z in terms of the product of x and y. So z does not play any role whatsoever. So now x, what was called x is v, and what was called y is v star, and I just combine the relation in such a way that then z is just 1 minus v star. That's what z in this is in this case. Okay, this algebra is it's an algebra which has a grading. Well, actually, it's graded by the cyclic group of order n, and it's also graded by integers. If you look at the grading, the Zn grading of this algebra, so you set the degree v equal to 1, so we want to have a grading compatible with a star, so the degree of v star is n minus 1, or minus 1 mod n. Right, and then we can see that the quantum cone algebra is actually a subalgebra of elements of degree 0. Okay, and here I wrote the embedding, how you can embed the algebra of the cone within the algebra of the disk, and this already tells us that we are in the setup of in this general setup of graded algebras. We have a graded algebra graded by a group, and we have a subalgebra which is the degree 0 subalgebra.
For Q equal 1 is cone algebra.
Well, it will be a cone.
It is a cone.
What is
N,
capital N is the level of the singularity that you have at the cone. It's a Zn singularity in this case. It's a type of the cone. It's getting sharper and sharper, if you like. Okay, so what I should say is that you should, in this game, you should never set Q equal to 1 because everything goes wrong. So, right, so now let's play the game of the general construction of this twisted real Dirac operator. So first what we need is the twisting, the automorphism. And automorphism is defined in this way. Okay, and this definition, so I mentioned, okay, so maybe I shouldn't mention this, or maybe I should mention this, that I mentioned that there are two gradings. I deliberately chosen to concentrate on one, but since I mentioned the other, I deliberately chosen to speak about one, not to create confusion, but now I am creating a confusion. So anyway, so we have this algebra automorphism, which will tell you that actually you can give this algebra Z grading, and the power of Q that appears under this automorphism will determine the grade of your element. Okay, so what can we tell about this automorphism? Well, first of all, this automorphism is star regular, so it satisfies this compatibility with the star. We can construct twisted derivations, which are written down here. So I wrote them on generators, and now you can, so there's del minus and del plus. You can trust me or look into our paper, our joint paper with Nicola, Ludwig, and Andrzej, and you will see that there is a proof that we can do, that we can extend it as this twisted derivation. And also this compatibility between the star structure, nu, and the derivations that we needed also holds. Okay, so we have, in this particular example, we have concrete twisted derivations. They are Q-twisted as needed. So I think this is all that was... oh, no, we need the selection of elements. Okay, so how do we select the elements, select the subgroups? Well, we just, as G plus, say, we just take 1 in our Zn, and just one element, the singleton set consisting of 1, and then G minus should be n minus 1, the inverse of 1 with respect to the addition mod n. Of course, for this to make these two algebras separate, actually we don't really need to. So I was. Who said that the groups should not overlap? You did. Okay. So that's it. Yes, I said because I am. You see, I am known being a person who likes to say yes, but.
That's true, especially after 10 p.m.
Yes. No. Yes. Okay. Anyway. Right. So. No, because what we can take the external direct sum. Okay, it's not the direct sum was not inside A, but you take a part of A. You know it's a module of B. You take another part. They might overlap or not. You take the usual direct sum of two modules, not internal inside a first module, but external direct sum, and there you go. You've got a module. So that's exactly what you can also take here. So. If there is no overlap between G plus and G minus, then this external direct sum becomes the internal direct sum. But in general, you can take the external direct sum.
But it was sort of like taking disjoint union.
Yeah, it's just like taking the disjoint union. Yeah. Okay, so you can take two copies of the same thing.
Exactly.
Okay, so. Right, so what we need, so I selected G plus, then this determines G minus. Now the action. The action is, so I can view elements of the cone algebra as elements inside the disk algebra, and then apply the automorphism. And if I do this, then I will get this twisted Dirac operator with twisted reality structure. And note that this there is really a twist there. The twist remains in this reality structure because nu squared restricted to the subalgebra is not identity. Okay, nu squared detects the if you think about the degrees of the of monomials, then it will detect the degree of the monomial. It takes the power of q. So if it's a monomial in Z, then you will have the power of q will tell you what was the degree of the monomial. But the fixed points are taken under the Z action, so there is a whole range of polynomials with degrees which are the multiples of n, which will be invariant under the Zn action. And still the nu will be non-trivial. Now what is interesting is that this system of two twisted derivations, maybe I should say nu squared there. So I was writing this last night, and last night maybe wasn't the best day for writing the... Yeah, but he wasn't in the... He didn't visit the brewery, so I don't know why.
At least not this one.
Well, at least not this one. Anyway, so there should be some squares, I think, nu squared. Okay, so this defines differential structure on all dq on the disk. Now, the differential structure that you will get in that way is not the standard differential structure on the disk. So if you go take the limit q equal to 1, you will not be able to satisfy the density condition. Okay, so it is not standard differential structure on D. on the disk, on the quantum disk. Now, from this point of view, the module of 1 forms when you restrict it to the subalgebra, OCNQ, or OCNQ viewed as a subalgebra. There are 2 copies of subspaces of degree 2, a copy of the degree 2 and degree minus 2. Okay, so you have some, in this case, you can actually talk about complex structure, and there is the holomorphic forms, anti-holomorphic forms. Everything lifts to the higher forms, so you can truly talk about complex structure in the sense of, for example, Masud, Kalkali, Gianni Landi, and Walter, with an easy name. Yes. Right. What one can see that this actually this Dirac operator it did not happen out of nowhere. So the differential, there is a connection between this differential calculus and the Dirac operator. That actually the differential for this calculus is represented by the commutator with D. And also, the Dirac operator is obtained by the Clifford action on a connection on the spinor bundle. So the spinor bundle in this case has this form. So that is, these are H plus and H minus as in before. And there is a connection which comes from the fact that we are dealing with the quantum principal bundle. So there is a strong connection. You can use it. You can construct this del there, and it has values in this particular differential structure. And then you can define this Clifford action, and your operator will be will coincide with precisely with this composition. Okay, so this was the case when the polynomial had no zeros. Now, when the polynomial has a single root at 0, then what we need to do, we reduce the polynomial by removing the root, so that we have p tilde of z. And then we construct another graded algebra, of which our generalized Weyl algebra will be a fixed point subalgebra, or the invariant subalgebra. And here I wrote the relations. And actually what it is an example of generalized Weyl algebra over extending the ring of polynomials in 2 variables. The variables here are z plus and z minus, so they will give you a polynomial ring, this commutation relation in 2 variables. And then you have a polynomial. This z is just the product of z minus z plus, or z plus z minus. So you have a polynomial in z plus and z minus. Automorphism, which changes the acts by the power of q. And write down the relation. This is exactly the Bavula's generalized Weyl algebra, now over the ring of polynomials in 2 variables. Okay, this is a star algebra if you define star operation in the way I described on the slide. Now, this algebra, particular cases, I don't know if I talk about this, probably not. Okay, so the particular case of this algebra is when you take p of z to be a quadratic polynomial. So p tilde of z is linear, and what you then recover are the relations of the SUQ2 group. Okay, so that's just the example up to the power of q convention. Okay, so this is a z-graded algebra, and or maybe I should say that if you go away from n equal from the quadratic polynomial, then what you will get will be a quantum length space. So this class of algebras includes interesting, or it corresponds to interesting examples of quantum algebras. Okay, this is a z-graded algebra, and I want to stick to z-grading here. Grading is compatible with the star operation. And we can recover the generalized Weyl algebra corresponding to polynomial p as a invariant subalgebra. Again, the grading is strong. You have a principal bundle, so you can construct the connection. Out of the connection, you can construct the Dirac operator in the same way as I described before. But coming from the graded algebra structure, what we have is we need to define this twist. So the twist is defined in that way. Okay, it's clearly compatible with the star. And but what you should note is that when we restrict it to the degree 0 part, this becomes identity map. Okay, so the resulting Dirac real structure for the Dirac operator will not be twisted. It will be just the twist will be the trivial one. Okay, and now we play the game of constructing. The most difficult part is to construct suitable derivations, Q derivations, and they are constructed in the following way. So again, you can trust me that they extend as Q derivations, where the CZ is the Q to the power 4 derivation of P tilde. Okay, so it looks quite complicated formula, but it's not that complicated. Anyway, okay, so you can check that this extends to the Q plus minus 2 Q derivations, nu squared, twisted, and so on and so forth, compatible with the with nu and the star structure. Now we select the sets G plus, G minus. For some reason, as a G plus, I took -1, and as a G minus is +1. We take the sorry, H plus, H minus. Well, we select subsets of the group. G plus is consists of -1, and our group is Z in this case. So obviously, the numbers -1 and 1 are not the same in Z. Okay. The representation is again as before, as the prescription tells us what it should be, but there is no nu there because nu acts as an identity on the elements of P. And we have the same procedure gives us the twisted Dirac operator, well, real Dirac operator with no twists there. Okay. At this stage, I could write all these relations without making any assumption about the Q separability of the polynomial. Now, where this Q separability really enters is when we try to interpret what we just constructed as a differential calculus. Okay, so first of all, this system of 2 derivations, Q derivations, can be supplemented by the third Q derivation on this large algebra. So you should think about this algebra as a 3-dimensional algebra over a 3-dimensional object. So if you want to have a good differential calculus, at least it has to have a dimension 3. So so you have this, and there is an way of defining this third Q derivation. And to show the density condition, you need to impose the Q separability condition. Okay, so that's where the Q separability enters, and that's why it fails in the classical case, because there would be repeated roots, no separability, except for the lowest dimensional, lower degree case, which corresponds to the sphere, or SU2. So you have a free calculus there. Okay, so in this way you obtain the differential calculus on all quantum length spaces, which extends in the smallest case. It's a differential calculus on the quantum sphere, defined 30 years now ago by Voronovich. And okay, if you look at the restriction of the module of 1 forms to the invariant subalgebra, then again it's a degree 2 and degree -2 part. So again we have some holomorphic and anti-holomorphic splitting, although I don't know what are the higher forms in general. As before, the differential can be represented by the commutator with D, and the Dirac operator is obtained by the Clifford action on composed with, in a way, canonical connection, which is defined on this quantum principal bundle. Okay, so that's the last slide, I think. Yeah. Nothing there. So, so the message that I would like you to take with you is that this class of generalized Weyl algebras, it's a very interesting class of algebras on which you can test a lot of ideas, in particular from Q geometry. And so Q geometry. And it is also a very interesting class of algebras from the, if you want to find a connection between non-commutative geometry a la Kohn and algebraic, non-commutative algebraic geometry a la Vandenberg Stafford. Because this is precisely the class of algebras that they are interested in, this algebraic side of non-commutative geometry. People are studying from algebraic geometry point of view. And this is precisely this class of algebras they are interested in. They are Calabi-Yau algebras with nice regularity, homological properties, and so on and so forth. And the second message is that you see, when n is not equal to 1 in those polynomials, if you go to the classical limit, you will get singular spaces. You will get orbifolds. Now, when you deform the orbifold, what you will get an object which behaves in many respects as a smooth object. And this is a very straightforward and down-to-earth illustration of the idea that there is a non-commutative way of resolving singularities. From the classical singular space, you introduce non-commutativity, and you end up with the non-commutative but non-singular space. And these algebras, from whatever point of view, the algebraic point of view, there is a different point of view of understanding what smoothness might mean in this algebraic setup. They are smooth in that way. So, okay. So, thank you very much.
Thank you. Time for questions, please.
So you mentioned already this was an algebraic tool.
Yes.
I'm curious about can you say something about summability properties, for instance, of this T?
Ludwig, can we say something?
Progress question.
Yeah.
So in this paper, this statement is about this part is algebraic. The other conformal is
So the paper consists, there are two examples. One is algebraic, and the other is the conformal transformation of the deformation of the Dirac operator. And in this conformal part, we start with the true Dirac operator and end up with all the conditions are there.
Well, so this is progress where you try to introduce the Hilbert space structure on H and so on.
Yes.
Ludwig, you wanted it.
Can I ask you, so this is not C star, but this is star, but if you take roots of 1, it doesn't make sense.
If you take, I haven't thought about it, about the star structure you would. I mean, I think it makes sense, and as long as these polynomials, the roots are separated, then things can be done. But if if you are unlucky and take your polynomial has a degree which is too large, and you have repeated roots, then there are problems. Because you can play exactly the same game for the. It's not a generalized Weyl algebra, but if you start with a torus and look at the non-commutative torus and Z2 action on it, and you will get a non-commutative pillow. Classically, it's an orbifold. If you in a non-commutative world, it's no longer an orbifold. Everything becomes really smooth, and you can take. I mean the Q is has modulus 1. It's a complex number of modulus 1, and only some roots of unity are excluded. I think 4 roots of unity are excluded.
Anybody else? Well, if not, I have 2 questions. First first is very concrete and other one's quite vague. So could you please go back to this case where you said, for n=1, it's just plot this here.
Yeah.
So, so plot list here has got a homogeneous space for SEQ2. When
Yes.
you go to these abile algebras, are they also homogeneous spaces for some quantum groups?
I don't know because they are the total spaces for the bundles or circle bundles that are defined here are length spaces which do not have group structure. Okay, so but I don't know whether they can be embedded into something bigger and I mean there is.
Yeah, but they're inside spheres which are inside quantum groups.
Yeah. So there is this interesting. I don't know whether you noticed there was a recent paper on Archive, or maybe it appeared when the conference was running, so we were busy with other things, of Uli Kramer, where he shows that if you have a classical variety, I think it's with a conical singularity, you can embed it into a Hopf algebra quantum group, so that it becomes a homogeneous space.
Wow.
So yeah, and this is particular example, but I think he mentioned that they have also other examples of this kind, and are trying to understand it. Maybe there is the way of solving singularity in this way, that you embed it into non-commutative, in the quantum group, and then you can say a bit more, view it as a homogeneous space, so you can say a bit more. And yeah.
And now my big question is as follows. You see, when you look at many of these algebras and you complete them to C-star algebras, they are usually graph C-star algebras. Now, if you now reverse this procedure and deprive these C-star algebras of norms, view them algebraically, but now with generators, they become Levitt-path algebras.
Yeah.
So would you have some bigger class of like Levitt-path algebras that could be part of this divide? I know that there's some fiddling with a Q. It's like sort of taking Q equal to 0, which
Which is
really
it's not really
for your purposes it's wrong,
from my purpose is wrong, because I wouldn't have the automorphism, so they wouldn't be examples of these Weil algebras. I don't think so. I don't think so, because the normal problem, maybe not a problem, but this Levitt-path algebras, they normally have quite a large number of zero divisors. They enter from this taking Q equal to 0. And so you would have to start, if you want to view it as a generalized Weil algebra, you would have to start with this base algebra would also have to be quite far away from being a domain, and so I don't know. So
algebraization of these.
yeah, it's a different. But these algebras are, as you say, when you complete them to C-star algebras, they are path C-star algebras. Graph C-star algebras. So Levitt-path algebras. Yeah.
Okay, if there are no more questions, let us do two things. First, let's thank Tomek again. And now we can do it together. I mean, this is so important that we really should do it carefully. We'd like to thank the organizers. Tomek thanks on behalf of speakers. I thank on behalf of everybody for inviting us to this beautiful city of Nijmegen, for arranging such great facilities, wonderful underground parking just under the terminal room, feeding us vegan food, taking us to the brewery, and also playing a movie, entertaining us with physics-flavored mathematics and mathematical-flavored physics. It was a lot of fun. It was absolutely great. Thank you guys and girls for everything. And when is the next meeting? Thank you.